Section 5.4, 2 3/4 members. What I'm going to show you now is how you can simplify your free body diagram analysis by recognizing 2 3/4 members. So suppose you have a member and is subjected to 2 forces only. Then I actually know the direction of those forces, because the rule is if a structure is subjected to 2 forces, they have to be collinear, equal, and opposite. Suppose I have a linkage that looks like that, and it was connected to another structure at those 2 points. I know exactly the direction of the forces at this point and this point. They have to be collinear, equal, and opposite. If they're not collinear, equal, and opposite, then the structure will not be in equilibrium. Suppose you have a structure that looks like this, and it's attached there. I know the direction of the forces at those 2 points. They'll be equal and opposite. Suppose you have a system that looks like this, and it was connected right there and right there. Then again, this is a 2 force member subjected to 2 forces, one here, one here. The reaction forces has to be collinear and equal and opposite. Let's say now we have a little more complicated system. Let's say we have a wall, it has a hinge, a beam connects to it like that, and we'll call this point A, we'll call this point B, where there's a force of 4 kilonewton that's applied. There's also a pin there, and it connects this linkage to the wall through this support like that. So this is a pin support, that's a pin support, that's also a pin support. So we can draw a couple free body diagrams of this particular system. One, I can separate this beam from this rod, and it would look something like this. And I'll draw that rod down here. Okay. So this is point A. We'll call this point D. We'll call this A, B, C, and D. So we'll call this D. We'll call this point B. And also this is point D. This is point C. So I have to draw the applied load of 4 kilonewtons. At A, this pin support prevents this beam from translating in the X. Therefore, I'll have a reaction force in the X direction. This pin support also prevents this beam from translating in the Y. So I'll have this reaction force in the Y. Now at D, this pin actually prevents this beam from translating in the X and translating in the Y. So I'd be tempted to draw a reaction force in the X and a reaction force in the Y. However, I should recognize that this is a 2 force member, and that would make the reaction force be collinear to one another but equal and opposite. So this force is equal and opposite to that. However, since D here is the same as the D here, I would have a reaction force such as that, and this would also be equal and opposite to this. And I'll know the actual direction of this angle because I'll know well, hopefully the problem statement gave us this angle. So it's not necessary to draw the unknown in the x and unknown in the y. That actually gives you two unknowns. Whereas recognizing that this is a two-force member, you can draw the reaction force at D only using one unknown. And in terms of static analysis, you want fewer unknowns as possible because it'll make it easier to solve. Now for three-force members. We also want to be able to recognize three-force members because it'll simplify your static equilibrium analysis. So here's a three-force member, and the rule is this. Let's say there's a force being applied right there, and let's say there's a force being applied right there and right there. So we have three forces, F1, F2, F3. So in order for this beam to be in equilibrium, these three forces must be concurrent. So I draw the lines of action for each of the force, and they should have this concurrent point. That must be satisfied. So now we know that this is in equilibrium. So when would a three-force member simplification become handy? Let's consider a system that looks something like this, where we have a support. It's pinned right there, and there's a linkage that gets connected like that. And there's also another linkage that's connected to it, and it's something like this, and it's pin supported here. All right, so for whatever reason they're actually applying a load of 400 newtons there. This is point A, B, and point D. So let's draw the free body diagram for this. And I can draw a free body diagram for BD. I can draw a free body diagram for BA. Or I can even draw the free body diagram for this whole entire system. Do an idealization. This would be DB. And I would also have, I'll call this A, and this will be B. So I have this 400 Newton force there. I recognize that this is a two-force member. If it's a two-force member, then I should draw it this way. Those are equal and opposite, so I'll call this F1, F1. I actually know the direction of this force, so I'll move it over here. So F1, and I know the direction. This B is the same as this B, therefore the reaction at B is equal and opposite to this F1, so it'd be like that. I also recognize that now this AB member is a three-force member because it's subjected to 1, 2, and 3 forces. So I actually know the direction of the reaction force at A. All I have to do is draw the line of action of the 400 Newton, draw the line of action of that F1. Therefore, the reaction at A would actually be in this direction. So I now know the reaction force at A. So let's see how many unknowns I have right here. I have F1 and A, because F1, let's see how many unknowns I have here. I have F1 and I have A. If we didn't make this simplification that this was a 2-force member and this was a 3-force member, then let's take a look at how many unknowns we would have. So here is DB, and here is my AB. So B, A, and I have this 400 Newton force there. So without making the simplification that this is a 2-force member, I will have to say that at the pin, the pin prevents member DB from translating in the X and Y. Therefore, it'll have a reaction in the X and Y. Same thing for point B. That pin prevents this member from translating in the X and Y. Therefore, I would have a reaction force in the X and Y. So I would have dx, dy, by, bx, if we're using this coordinate system. Same thing right here. I would have equal and opposite, bx, and since by is going up, I make it go down. And at A, that pin support prevents AB from translating in the X and Y. Therefore, there would be a reaction in those directions. So I would have AY, AX. Okay, so that's my free body diagram. So let's look at how many unknowns I have. I have AX, AY, BX, BY, dx, dy. So if we didn't recognize that this was a 2-force member and this was a 3-force member, we would have 1, 2, 3, 4, 5, 6 unknowns. But if we did recognize it, we would only have 2 unknowns.